Okay. Oh, nope, doesn't say 8 o'clock yet. My notebook. Okay, now it's 8 o'clock. Good morning, everybody. Let's see. I posted your homework that's due the 30th. Well, actually, I didn't do it till yesterday. I almost forgot. but yeah, your new homework assignment is up. The Friday after November 30th, which will be November 6th, I think. Well, first Friday in November is your third exam. Okay. But this week you have homework due. That means next week you will not have homework due because you will have an exam. Any questions?
Homework will not be due next week for what reason again? Exams?
Because you do not have homework due the week you have exams.
Okay, so there's an exam next week.
That's right. Every week you hand in something, okay? When you hand in an exam for 1 week, you not have homework due that week, but every other Friday you do. Okay. All right, so let's start class. We started talking about antiderivatives on Friday. Let's talk a little bit more about that. Yeah, we're starting sort of the final third portion of the course here. Okay, and that's my 2414. All right, so let's see. Antiderivatives. So instead of going from a function and taking a function and then taking its derivative, okay, we're going to go the other way. We're going to take a function and find what is the derivative of. So thinking backwards. Okay, suppose you have 4 functions, capital F, little f, capital G, and little g, and capital F prime is little f, and capital G prime is little g, and c is a constant. Then because of the way the derivative rules work, if we go backwards with those, we get the following rules for antiderivatives. If you have a constant times the function little f, its antiderivative is going to be that constant times big F. Okay. Big F is the antiderivative of little f, or an antiderivative. If you have the sum of 2 functions, little f and g of f, no, little f and g, okay, so f of x plus g of x, a particular antiderivative of that sum is big F of x plus g of x. And this is the next one's a more general rule. If you have x raised to a power, and that power is not equal to -1, and that n is fixed, it's not varying, okay, then the antiderivative of x to the n is x to the n plus 1 over n plus 1. And then because the derivative of the sine of x is the cosine of x, that means an antiderivative of cosine of x is sine of x. Likewise, since the derivative of the cosine of x is minus the sine of x, and antiderivative of sine of x is minus the cosine of x. Antiderivative of secant squared is tangent of x, and antiderivative of secant x times tangent x is the secant of x. And antiderivative of cosecant squared is minus cotangent of x. And antiderivative of cosecant x times cotangent x is minus cosecant x. And then, okay, the inverse trig functions, going backwards again. Since the derivative of arctangent of x is 1 over 1 plus x squared, and antiderivative of 1 over 1 plus x squared is arctan of x. And since the derivative of arcsine of x is 1 over the square root of 1 minus x squared, and antiderivative of 1 over the square root of 1 minus x squared is arcsine of x. And there are others you could add to this list. Okay, these are basically just taking derivative laws and going backwards with them. Okay, so any question about any of those rules? Okay, then let's work. This is a ball problem, ball thrown upward. Okay. And this time I'm not going to have to give you the model. Okay. So a ball is thrown upward with a speed of 48 feet per second from the edge of a cliff that's 432 feet above the ground. And we're assuming the ball, okay, is thrown up, so it goes up for a while, and then it comes back down, right? Because of gravity. Yeah, we're on the Earth. We want to find its height above the ground t seconds later. And of course, at some point, it's going to come back and hit the ground, at which point our problem's over because who knows what happens then. Does it bounce? Does it fall in some water or whatever? When does it reach its maximum height? And when does it hit the ground? Okay, in this problem, we're neglecting some things, a lot of things. We're neglecting air resistance. We're assuming the wind's not blowing and making this not be motion in a line, basically. And we're going to assume that acceleration is 32 feet per second squared. And this is acceleration due to gravity. Okay. Acceleration is a constant 32. And well, there's another assumption here. We have to pick out a coordinate system, basically. We're going to assume that the positive direction is up. And the negative direction is when you're falling towards the ground. Okay. Well, with those assumptions, acceleration is 32 feet per second squared, but acceleration, okay, it's pulling, well, it's okay, gravity is a force, and it's pulling things towards the ground. And that's the negative direction. So acceleration here is minus 32. And this is in the English system. Measuring height in feet and time in seconds. Okay. So acceleration is a constant minus 32, and acceleration is also the second derivative. Okay. It's f double prime, where s is going to be our equation, our position function. Tells you how high, yeah, s is going to tell us how high above the ground the ball is at time t. All right, so the second derivative is minus 32. And to get the first derivative, we take the antiderivative, or an antiderivative of minus 32. Well, so s prime, which is going to be velocity, is minus 32t. And we get an arbitrary constant. Okay. Yeah, if you take a function little f and you look at its entire family of antiderivatives, well, if big F is a particular antiderivative, so is big F plus any constant. And that's why I'm putting on that C. If minus 32t is an antiderivative of minus 32, so is minus 32t plus c, where c is a constant. And in fact, I don't want to assume that c is equal to 0, which is what you're doing if you don't write it at all. I need to know which c is needed here. So I just write C to indicate that any constant there would work as far as the antiderivative goes. Okay, so yeah, I need to know what C is and what's going to tell me about that. Well, let's go back to the problem. It says a ball is thrown upward, that's in the positive direction, with a speed of 48 feet per second. So that's your velocity when the problem starts. This says this is at time 0 when the problem starts. Okay, so that says that the velocity at time 0 is 48. Upward is a positive direction, remember. So V at 0 is 48, and S prime of t, which is V of t, is minus 32t plus some constant. And that says, putting in 0, okay, putting in 0, which means instead of t, I'm writing 0, okay. But B at 0 is also 48. That's given as part of the problem. So that says, well, 32 times 0 is 0. That says that C is 48. Okay, so that's the constant I need for this problem. So now we've completely determined S prime and velocity. S prime, which is the same thing as the velocity. Okay. Oh, put it here. So S prime of t equal to V of t is minus 32t plus 48. Okay. And that's our first derivative. So we take any derivative again to get to the position function. Okay, any derivative of minus 32t would be, okay, well, minus 32, that's just a constant. And then we need the antiderivative of t. Well, that's t to the first power. So you use this rule. If you have x to the n, the antiderivative is x to the n plus 1 over n plus 1, as long as n is not equal to minus 1. Well, here n is 1, so n plus 1 is 2. The antiderivative for t is t squared over 2. And then an antiderivative for 48. Okay, and these functions are added, so we can add their antiderivatives. That was in our list above. And we get another constant, d. Okay, another arbitrary constant. But so far, we have that our position function, our height function, is s of t times minus 32, t squared over 2 plus 48t plus d. We can simplify that a little bit. That's minus 16t squared plus 48t plus d. And you might notice a lot of those motion problems before had that minus 16 in them. That's where it comes from. It comes from your assumption about the gravitational constant being 32, okay, in the English system. In the metric system, it's 9.8 kilometers per second squared. So it matters whether you're in the metric system or the English system. But okay, so we've got the height function determined, except for this constant, which we need to know. Okay, and what's going to tell us about what d is? Well, back to the problem. Okay, here's where we're going to use this piece. From the edge of a cliff that's 432 feet above the ground. So when you start the problem, you're up at a level of 432 feet. Yeah, here's my little picture. Okay, here's the cliff, and this height is 432. This height right here. Here's the ground down there. Our height at time 0 is plus 432. So we're given S at time 0 is plus 432. Okay. All right, that's going to allow us to find D. S at time 0, and let me switch back to black writing. I think I'm going to get shortly a better note program, but I've got to download it, and then I'll make sure I know how to use it before I start doing it. It'll keep better files than this one does, but that's beside the point. Okay, S at time 0 is 432. But S at time 0, okay, I can also get it from what I've got here for my antiderivative. It's also minus 16 times 0 squared plus 48 times 0 plus d. And okay, those are zeros. So this is just equal to d. D is 432. And that says then I've completely determined my height function. S at t is minus 16t squared plus 48t plus 432. Okay. Any questions so far? Can y'all still hear me?
Yes, ma'am, we can.
Okay, thank you for responding. Yeah, I remember when my microphone went out once. Okay, so let's see. So our questions then. We've got our position function, our height function determined. What were the questions? Find its height above the ground t seconds later. Well, we've done that. That's what S is. So S of t, given a time before the ball hits the ground, okay, the height of the ball is 48. Where'd I get that? Is the height. Is the height S of t of the ball at time t until it hits the ground. We've got the first part of the problem done. Second thing it asks, when does it reach its maximum height? Okay. Well, if it's asking for a maximum, that means we need to know what the derivative is because we need our critical points. You find the maximum, local minimum, the local minimum, local maximum, they happen at critical points. And in this case too, well, this is over a finite interval of time. So, well, the minimum height of the ball is going to be 0, right? That's going to be when it hits the ground. But what's the maximum height? That's going to occur when S prime of t is 0. And that makes sense. Okay, that's what we did with our calculus before. Find a critical number, but think about what this ball is doing. Okay, here's my diagram. You throw it up with an initial velocity of 48 feet per second. Okay, so it's going up, 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 up. But gravity's pulling on it and trying to make it come down. So as it goes up, it slows down. Its velocity decreases. When it hits the maximum height, its velocity is 0. And then its velocity starts decreasing and becomes negative, in fact, okay? Because now the ball's moving in the negative direction. Positive direction is up. Positive is up. Negative is down. So that kind of makes sense just looking at the picture too. Okay, so that means I want to set S prime equal to 0. S prime, remember what S prime was, minus 32t plus 48. Equal to 0. So that says 32t is 48. T is 48 over 32. And that's 3 over 2. Because 16 times 3 is 48. And 16 times 2 is 32. So t equals 3/2 second. Okay. And well, let's see. Okay. And let me check my intervals. There is going to be a finite interval involved here, but all right. I don't know when that last number is because that's the answer to the third question. All right. So we have t. Nothing makes sense before 0. Okay. Nothing was. The problem only started at time 0. But we have our only critical number is at 3/2. I could pick 1 to check because it's between 0 and 3/2. And I would get minus 32 plus 48. That's positive. Ball is going up. After 32, say, well, hopefully before it hits the ground. Okay. 2, say would be over there. That would give me minus 64 plus 48. That's a negative number. Ball's coming down. Okay, so the maximum height is S of 3/2 because that's a local maximum. Okay, ball comes up, ball goes down. Local max. That also makes sense just from the problem. All right, so we need S of 3/2, and S was minus 16t squared plus 48t plus 432. Okay, and I'm putting in t equal to 3/2 minus 16 3/2 squared plus 432. Ugh, arithmetic. Okay, so let's see. Let's grit our teeth and do it. That's minus 16 times 9 over 4. And then 48 over 2 is 24. And 16 over 4 would be 4. So this is minus 36. Check my arithmetic, please. Plus 72 plus 432. And let's see, let's add. That'd be 4, 10, 1 is 5. 432 plus 72. Okay. And then I want to subtract 36. 14 minus 6 is 8. 9 minus 3 is 6. 468. Okay, so 468. So the maximum height, 468 feet above the ground. Okay. And the last question is, was when does the ball hit the ground? Well, that's when the height is equal to 0. Let me answer this question. It's when the height is 0. We know what the height function is. Okay. So let's answer that last question. That's okay, that's basically when S of t is 0. So that says that 0 is S of t is minus 16 t squared plus 48t plus 4 to 32. And that's equal to, okay, well, let's see. Okay. You can always use the quadratic equation to solve a quadratic equation. Okay. The quadratic formula, excuse me, quadratic formula. But let's see, I can see if I can clean it up some first. I think I can factor a 16 out of this. Make sure it's a factor of 432. Goes twice. 1, 1, 2. 16 goes 7 times. 7 times 6 is 42. Yeah, 27 times. Okay, so I can factor out a 16 minus t squared. Now watch me on this. Okay. Make sure I don't mess something up. So easy to have a minus turn into a plus or vice versa. Okay, so if I factor that 16 out, and that means 0 over 16, which is 0. And then also, how about I put the minus in there? And let's see. I'm not sure that factors. I don't think it factors very nicely if it does. 9 times 3. No, so you can get 3 out of that. Okay, quadratic formula. T would be minus b. You have okay, that over there to the side. T would be minus b, which would be plus 3, plus or minus the square root of b squared would be 9, minus 4 times a, which is 1, times c, which is minus 27. Okay, which is at least a positive number. So that means they're going to be roots over 2a, which is 2. So let's see. So 4 times 27 Better high factor. Okay. If I factor first, I won't have so much arithmetic to do. I've got a 9. Okay. Let's write several steps. I've got 9 plus 4 times 27 under the radical. And 27 has a factor of 9. Okay, so I factor a 9 out of that term, under that expression on the radical. So 1 plus 4 times 3. Don't forget that 2. So square root of 9 is 3. And then I have what's left in there. 1 plus 12 is 13. Okay. So I've got t equal to 3 halves, and there are two possible t's. Only the -1 doesn't make any sense here because it'd be negative. T equal to 3 halves minus 3 halves times the square root of 13 is less than 0. So I can eliminate that. It's not possible, not when t starts at 0 for the problem. So that means we only get 1 t. Which I could write as 3 halves times 1 plus the square root of 13. So the ball hits the ground at t equal to 3 halves times 1 plus the square root of 13 seconds. And that's how I want you to leave your answers, actually. Now, okay, you may feel, and in some cases, you really do need a numerical approximation of that. That's about, very roughly, it's about 6.9 seconds. So after the problem starts.
Okay. It says, oh wait, you factored out the whole thing. I'm sorry. I was trying to figure out where you got 3/2 outside of 1 plus 13. Then I looked at it again and it's like, wait, oh, hold on. She factored that out.
That's right. That's what I did. Okay. Okay. Any other questions?
I derped a second.
Okay. Yeah. So now, actually, you can do motion problems. We can only handle motion basically along a straight line. And our straight line here, the ball went up and then it came down. Okay. It didn't get shut off at an angle or something. You're not going to be able to handle those until next semester or maybe even later. But now we don't have to be given the equation of motion. You can actually derive it from your assumptions by using this idea of antiderivatives. Okay, let's see. What time is it? 38 after. I still got 20 minutes. Let's just do some practicing. Okay, finding these antiderivatives. Now, we can't just do anything. Take any whole f and find its antiderivative. In fact, you never will be, okay, able to do that. Even though we're going to have theorems that tell us that as long as a function is continuous over an interval, it has an antiderivative. Doesn't mean you can write it down in what you call elementary terms. That is in terms of the functions we know about, sines, cosines, polynomials, rational functions, exponentials, logs, and combinations of those. Even though it has an antiderivative, you can't write it in terms of those sort of functions that we commonly deal with. But we can do a lot now even, and over the rest of this semester and the first third of next semester, you're going to learn a lot more about this. Okay, so let's find and your homework this week has, well, okay, I think I gave you, oh, well, here it is right here. I gave you 4 more optimization problems, and then the rest of them are antiderivative problems. This week's homework's not going to take nearly as much time as last week's did. But you should still get started early, okay? Make sure you understand. Find the most general antiderivative. Yeah, and after today, you're going to be completely ready to do your homework problems, all of them. Also, this is where your third exam stops, okay? Because this is the last homework that will be due before the third exam. Okay, so here's one. Okay, so we want the most general antiderivative. It helps to write this square root of t in exponential notation, okay? So capital F of t, and I'm naming capital F of t the antiderivative, capital F prime of t is little f of t, would be, okay, antiderivative of t, what's that going to be? Anybody?
Well, the first t would be 1/2 times t squared.
Okay. Yes. T squared over 2. And what rule is that? This is t to the first. So that means the antiderivative would be t to the n plus 1 over n plus 1, right? The rule is for x to the n, the antiderivative is x to the n plus 1 over n plus 1. And of course, that assumes n is not equal to minus 1. Okay, so for t, antiderivative is t squared over 2. And we've got functions basically added there. So well, the minus is just minus 1, the constant. But I can just take the antiderivatives and put them back in as a difference of the antiderivatives for the big antiderivative. Okay, what's the antiderivative of t to the 1/2? That's a 1.
Would it be t to the power of 3 over 2 all divided by 3 over 2?
Yeah, thank you. So t to the 3 over 2 divided by 3 over 2 plus c. And okay, I could do a little algebra there. So t squared over 2, that t 1 over 3 has would be 2/3. Okay. So there's your antiderivative. Pretty straightforward. Let's see, try another one. Let me pick one out here. How about this problem? So you have four minus 3x to the 4th plus 2x to the 6th all over x to the 6th. Well, that's a quotient of two functions. And going back to our rules at the first, I don't see anything in that list that tells me how to deal with a function that's a quotient of two functions. To go way back to the start. Okay, here's our list. I know how to handle a constant times a function. Let's see, let's do u. Okay, so a constant times a function, just the constant times antiderivative. Two functions are added, sum of the antiderivatives, x to the n plus 1 over n plus 1, then the trig functions and the inverse trig functions. But there's nothing about what to do with something that's like f over g, right? Nothing on this side that would tell you about how to deal with this situation. Okay, so I can't deal with it right now. What can I do? Well, I can try to write the function in another form and without changing the function. Okay, and I can do that in this case. That denominator only has one term in it, so I can break the fraction up into the sum of three fractions. This is 4 over x to the 6th minus 3x to the 4th over x to the 6th plus 2x to the 6th over x to the 6th. And that's equal to, okay, well, it'd be better if I had these x written in the form x to the n. But I can do that. What's 4 over x to the 6th equal to?
Wouldn't it be 1 over x squared?
Oh, I think you did too many steps at once. Okay. Okay. How about, we haven't taken the antiderivative yet, right? So 4 over x to the 6th, I'm just still changing the form of the function. So this would be 4x to the minus 6. That was kind of what I was looking for. The first term here I can rewrite as 4x to the minus 6. How can I rewrite the next term? Just doing algebra here. What's x to the 4 divided by x to the 6 equal to? Okay, no answers. Be x to the minus 2. right? Using the rule, a to the r over a to the s is a to the r minus s, that algebra rule. And then 2x to the 6 over x to the 6 is just 2. Okay, so I rewrote g. Now, well, okay, you're lucky if you can do that. But begin with this problem. Instead of having it written as a quotient, I now have it written as a sum of functions. And now I can use the few rules we have so far. So the antiderivative, I did put my C, good. Okay. The antiderivative, we're calling it capital G of x, would be 4x. Okay, it's for x to the n, the rule is it's x to the n plus 1 over n plus 1. Be using that. So 4x to the minus 6 plus 1 over minus 6 plus 1. Minus 2 plus 1 over minus 2 plus 1, that's right. Plus 2x plus a constant. So the minus 4 over 5. That's minus 1 there. So minus 1 divided by minus 3 is plus 3. Okay, so minus 4/5 x to the minus 5th plus 3x to the minus 1 plus 2x plus c. Any questions? Can y'all still hear me?
Yes, ma'am.
Okay, thank you. Okay. One more. We're almost out of time. If I have, how about this? Okay, this is kind of tricky. H of theta is sine of x of theta. Theta's my variable. Okay, that's another quotient. Okay. I have no rule in our list so far that tells us how to deal with it. So I'm going to try to rewrite it. Sine of theta over cosine square of theta. I can write that as sine of theta over cosine of theta times 1 over the cosine of theta. Well, sine over cosine is tangent. 1 over cosine is the secant. And secant theta, tangent theta, that's in my original list. Okay. Way back here first. It is right there.
So the antiderivative of secant x tangent x is secant x.
Right. And so my derivative is secant theta, tangent theta. Oof, down here somewhere. So capital H of theta would be secant of theta. And you still get to add a constant. Okay, well, we are out of time. And let's see, tomorrow we're going to start some new stuff. Now, your exam ends here with this material.
About the exam, I had a couple of questions actually.
Okay, well, let's see. Let me end class. So anybody that needs to go can go. And stick around if you have questions. And Mr. Drake, okay, what's your question?
Two questions. First, the exam is going to be on Friday, just like all the others, right? Friday of next week. I know it's a fairly stupid question, but yeah, I just want to be 100% sure. Hello?
I think she really in the class.
I know she did. She said she was going to, but